Imagine the Milky Way as a cosmic toddler, flailing through its infancy, its gravity still learning to hold together the chaos of its birth. For decades, astronomers stared at the galaxy's halo, its ancient, diffuse glow, and saw only a faint, puzzling signal. It wasn't until Hubble's razor-sharp eye pierced the veil of time, peering 13 billion years back, that the truth emerged: a hidden merger, a silent collision with a dwarf galaxy so violent it left behind a ghostly trail of stars, reshaping the Milky Way structure. This wasn't just a discovery, it was a revelation, rewriting the story of how our galaxy grew from a turbulent, starry cradle into the spiral we call home. For centuries, astronomers have gazed at the night sky, wondering how our Milky Way galaxy came to be. The vast spiral of stars, gas, and dark matter that we call home is a complex tapestry of cosmic history, and one of the most intriguing questions has always been, how did the Milky Way grow to its current size? Recent discoveries, made possible by the Hubble Space Telescope, have shed new light on this mystery. It turns out that the Milky Way's early years were marked by a dramatic event, a massive merger with a smaller galaxy that left a lasting imprint on its structure. This discovery, announced in 2023, has rewritten our understanding of how the Milky Way formed and evolved. Let's explore what this means for the story of our cosmic home. The Milky Way is not a static, isolated system. It has always been part of a dynamic universe, where galaxies collide, merge, and reshape themselves over billions of years. Mergers are a fundamental part of galaxy evolution, and the Milky Way is no exception. However, the details of its early history have remained elusive. For decades, scientists have debated whether the Milky Way's growth was driven by a series of smaller mergers or a single, dramatic collision with a massive neighbor. The new findings from Hubble suggest that the latter is true. A massive merger with a smaller galaxy billions of years ago played a crucial role in shaping the Milky Way as we know it today. To understand this discovery, we need to step back and consider how galaxies form. The Milky Way, like most large galaxies, is thought to have begun as a relatively small, dense cluster of stars. Over time, it would have grown by accreting gas, stars, and dark matter from its surroundings. But mergers with other galaxies are also a key mechanism for growth. When two galaxies collide, their stars and gas interact, leading to dramatic changes in their structure. In some cases, the collision can trigger intense star formation, while in others, it can completely reshape the galaxy's shape, turning a spiral into an elliptical or even a ring-like structure. For the Milky Way, the most significant merger in its history is believed to have occurred around 10 to 13 billion years ago. This event, now known as the Gaia-Sausage merger, involved a smaller galaxy, likely a dwarf galaxy, colliding with the early Milky Way. The dwarf galaxy was not as massive as the Milky Way itself, but it was large enough to leave a profound impact. The collision would have been a slow, chaotic process, as the two galaxy stars and dark matter intertwined. Over millions of years, the smaller galaxy would have been torn apart by the Milky Way's gravitational pull, with its stars and gas being pulled into the larger galaxy's halo. This process is similar to how the Milky Way is currently absorbing the dwarf galaxy Andromeda, though on a much smaller scale. The key evidence for this merger came from the distribution of stars in the Milky Way's halo, the vast, diffuse region of stars that surrounds the galaxy's central disk. The halo is a critical component of a galaxy's structure, and its composition can reveal a lot about a galaxy's history. In the case of the Milky Way, the halo contains a mix of old stars, many of which are believed to have originated from the Gaia-Sausage merger. These stars are not uniformly distributed; instead, they form a complex, irregular pattern that suggests they were pulled into the Milky Way from an external source. This pattern is distinct from the more uniform distribution of stars in the Milky Way's disk, which are thought to have formed in situ over time. One of the most compelling pieces of evidence for the Gaia-Sausage merger comes from the velocities of these stars. When galaxies merge, the stars from the smaller galaxy retain a distinct kinematic signature, meaning they move in a way that is different from the majority of the Milky Way's stars. By studying the motion of stars in the halo, astronomers have found that a significant portion of them have velocities that don't align with the overall rotation of the Milky Way. This suggests that these stars were not born within the Milky Way but were instead pulled in from an external galaxy. The Hubble Space Telescope played a crucial role in confirming this by providing high-resolution data on the positions and velocities of these stars, allowing scientists to trace their origins back to the merger event. The implications of this discovery are profound. For years, scientists believed that the Milky Way's halo was primarily composed of stars that formed within the galaxy itself. However, the Gaia-Sausage merger shows that a significant portion of the halo's stars were added through external mergers. This means that the Milky Way's structure is not just a product of its own evolution but also the result of violent cosmic collisions. The merger also likely contributed to the Milky Way's current shape. The chaotic interaction between the two galaxies may have disrupted the early Milky Way structure, leading to the formation of the disk we see today. Additionally, the merger could have triggered bursts of star formation, as the gravitational interactions between the two galaxies compressed gas clouds, leading to the birth of new stars. Another fascinating aspect of this discovery is the role of dark matter in the merger. Dark matter, which makes up the majority of the Milky Way's mass, plays a critical role in galaxy formation and evolution. During the merger, the dark matter from the smaller galaxy would have been pulled into the Milky Way's halo, forming a complex web of dark matter that still exists today. This dark matter halo is invisible to us, but its gravitational influence can be detected through the motion of visible stars. The Hubble observations helped map the distribution of this dark matter, providing further evidence that the merger was a significant event in the Milky Way's history. The Gaia-Sausage merger also has implications for our understanding of the Milky Way's future. The Milky Way is currently on a collision course with the Andromeda Galaxy, a process that is expected to take about 4 billion years. While this merger will be a significant event, it is likely to be less dramatic than the Gaia-Sausage merger. The Andromeda merger will involve two large galaxies colliding, but the Gaia-Sausage merger was a smaller galaxy merging with a much larger one. The differences in scale and timing mean that the two events will have different effects on the Milky Way's structure and star formation. The discovery of the Gaia-Sausage merger also highlights the importance of long-term observations in astronomy. The Hubble Space Telescope has been instrumental in tracking the motion of stars in the Milky Way's halo, allowing scientists to piece together the history of these stars. Without the high-resolution data provided by Hubble, it would have been much more difficult to detect the subtle signatures of the merger. This underscores the value of sustained observational efforts in unraveling the mysteries of the universe. In conclusion, the Hubble Space Telescope has provided critical insights into the Milky Way's early history, revealing that a major merger with a smaller galaxy played a pivotal role in shaping our galaxy. This discovery has reshaped our understanding of how galaxies evolve, demonstrating that mergers are a fundamental part of the cosmic dance of galaxy formation. The Gaia-Sausage merger not only contributed to the Milky Way structure and star formation but also left a lasting imprint on its halo, a region that continues to reveal clues about the galaxy's past. As we continue to study the Milky Way and other galaxies, we are uncovering the intricate story of how the universe has evolved over billions of years, with mergers playing a central role in the formation of the galaxies we see today. For decades, astronomers have puzzled over the Milky Way's origins. How did our galaxy form? What ancient events shaped its structure? Recent discoveries suggest that a dramatic cosmic collision between the Milky Way and a smaller galaxy played a key role in its evolution. But how did scientists uncover this hidden history? The answer lies in a combination of cutting-edge technology, meticulous observation, and a deep understanding of how galaxies grow. At the heart of this revelation is the Hubble Space Telescope, an instrument that has spent over 3 decades peering into the universe's past. But solving this mystery required more than just Hubble's powerful eye. It demanded a collaborative effort spanning years of data collection, advanced computational modeling, and a willingness to rethink long-held assumptions about galaxy formation. The story begins with a surprising observation: the Milky Way's stellar halo, a vast, diffuse region of ancient stars surrounding the galaxy, contains a population of stars that don't quite fit the expected pattern. These stars, known as the thorny population, have chemical compositions and motion patterns that suggest they originated from a different galaxy. But identifying the source of these stars required more than just cataloging their properties. It demanded a way to trace their movement through time, to determine whether they were part of a long-lost companion galaxy that had been absorbed by the Milky Way. This is where the Gaia mission came into play. Launched by the European Space Agency in 2013, Gaia has been mapping the positions, distances, and velocities of over 1 billion stars in our galaxy with unprecedented precision. By analyzing the motion of these stars, scientists could detect subtle deviations from the Milky Way's normal rotation, hinting at a massive gravitational disturbance in its past. But Gaia's data alone couldn't reveal the full story. To understand the nature of this disturbance, astronomers needed to determine whether the star's unusual motion was due to a recent event or an ancient one. This is where Hubble's unique capabilities became essential. Unlike ground-based telescopes, which are limited by atmospheric distortion, Hubble's position above Earth's atmosphere allows it to capture images with incredible clarity. Its Advanced Camera for Surveys (ACS) and Wide Field Camera 3 (WFC3) have been instrumental in studying the Milky Way's stellar halo, enabling scientists to distinguish between stars that are part of the Milky Way and those that might have been pulled in from another galaxy. However, Hubble's role went beyond imaging. By analyzing the light from these stars, astronomers could measure their velocities using a technique called spectroscopy. This involves splitting starlight into its component colors, which reveals the Doppler shift, how much the light is stretched or compressed due to the star's motion relative to Earth. These velocity measurements, combined with Gaia's positional data, provided a three-dimensional map of the Milky Way's stellar population, allowing scientists to trace the paths of stars and identify those that had been displaced by a past merger. The challenge, however, was not just in collecting data, it was in interpreting it. The stars in the thorny population had velocities that suggested they were moving in a way inconsistent with the Milky Way's normal rotation. But how could scientists determine whether this was the result of a recent collision or an ancient event? The answer lay in simulations. By running computer models of galaxy mergers, astronomers could test different scenarios and see which one best matched the observed data. These simulations required immense computational power, relying on supercomputers to model the gravitational interactions between millions of stars over billions of years. The results were striking. The best-fitting model suggested that the Milky Way had collided with a smaller galaxy approximately 10 billion years ago. This collision, known as the Gaia-Sausage merger, had injected a vast number of stars into the Milky Way's halo, leaving behind a distinct signature in the distribution of stellar velocities. But even with these simulations, the question remained, how could scientists confirm that this merger had actually occurred? The answer came from a combination of observational evidence and theoretical modeling. By comparing the predicted motion of stars in the Gaia-Sausage merger with the actual velocities measured by Hubble and Gaia, scientists found a remarkable match. The stars that had been pulled into the Milky Way during the collision exhibited a unique pattern of motion, one that could not be explained by any other process. This pattern, known as the radial velocity dispersion, provided direct evidence that a massive galaxy had once been torn apart by the Milky Way's gravity. Moreover, the timing of the merger aligned with the expected timeline for the Milky Way's formation. The Milky Way is believed to have formed around 13 billion years ago, and the Gaia-Sausage merger occurred roughly 10 billion years later, when the galaxy was still in its early stages of growth. This timing suggests that the merger was a pivotal event in the Milky Way's evolution, helping to shape its structure and influence the distribution of stars in its halo. The process of solving this mystery was far from straightforward. It required overcoming several technical and theoretical hurdles. One of the biggest challenges was distinguishing between the motion of individual stars and the overall rotation of the Milky Way. Since the galaxy itself is rotating, many stars appear to move in a way that could be mistaken for the effects of a merger. To address this, scientists used a technique called kinematic decomposition, which separates the motion of stars into components that are due to the galaxy's rotation and those that are due to external forces like mergers. This method allowed them to isolate the peculiar motion of the thorny population, confirming that their velocities were indeed anomalous. Another challenge was accounting for the vast distances involved. The stars in the stellar halo are located millions of light-years away, making it difficult to measure their velocities with sufficient precision. Hubble's spectroscopic capabilities, combined with Gaia's positional data, provided the necessary accuracy to overcome this limitation. The collaboration between Hubble and Gaia was also crucial. While Gaia provided a broad overview of the Milky Way's stellar population, Hubble's high-resolution imaging allowed scientists to study individual stars in detail. This dual approach enabled a more comprehensive understanding of the merger's impact. For example, Hubble's ability to detect faint, ancient stars in the halo helped confirm that the Gaia-Sausage merger had occurred at a time when the Milky Way was still young and actively forming. These stars, which are older and less metal-rich than those in the galaxy's disk, provided a clear signature of the merger's timing. Additionally, Hubble's observations of the Milky Way's satellite galaxies, such as the Large and Small Magellanic Clouds, offered further insights. These galaxies, which are still orbiting the Milky Way, may have been part of the same ancient merger event, suggesting that the Gaia-Sausage merger was part of a larger process of galaxy assembly. The implications of this discovery extend beyond the Milky Way. By studying how our galaxy formed through mergers, scientists can gain a better understanding of how galaxies in general evolve. Mergers are a fundamental process in galaxy formation, yet they are difficult to observe directly because they occur over billions of years. The Gaia-Sausage merger provides a rare opportunity to witness the aftermath of such an event in our own galaxy. It also highlights the importance of long-term observational campaigns like Gaia and Hubble, which have provided the data necessary to piece together the Milky Way's history. Without these missions, the evidence for the merger would have remained hidden, buried in the vastness of space and time. As scientists continue to analyze the data from Hubble and Gaia, new questions are emerging. For example, how did the Gaia-Sausage merger affect the distribution of dark matter in the Milky Way? And what role did other smaller mergers play in shaping the galaxy's structure? These questions underscore the complexity of galaxy formation and the need for ongoing research. The discovery of the Gaia-Sausage merger is not the end of the story, it is a milestone in our quest to understand the universe. It reminds us that even in the vastness of space, the echoes of ancient collisions still linger, waiting to be uncovered by the tools of modern astronomy. Hubble solves merger mystery from Milky Way's early years. This part of our deep dive into Hubble solves merger mystery from Milky Way's early years focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. Hubble solves merger mystery from Milky Way's early years. This part of our deep dive into Hubble solves merger mystery from Milky Way's early years focuses on, give historical context, how our understanding of this general topic evolved over past decades, earlier missions, or discoveries that led up to this moment. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. The Hubble Space Telescope's discovery of a star-forming region in the Milky Way's early history has opened a window into a cosmic mystery that has puzzled astronomers for decades. This region, dubbed the starburst, is a dense cluster of young stars that formed around 10 to 12 billion years ago, a time when the Milky Way was still in its infancy. But the true intrigue lies not in the stars themselves, but in the event that triggered their birth. Scientists believe this burst of star formation was likely the result of a violent cosmic collision, a merger between the Milky Way and another galaxy. Yet, even with Hubble's groundbreaking observations, many questions remain unanswered. What exactly happened during this merger? How did it shape the Milky Way we see today? And why does this event still defy complete explanation? These are the open questions that continue to fuel scientific debate, reminding us that even with the most advanced tools, the universe still holds mysteries beyond our grasp. One of the most pressing mysteries is the identity of the galaxy that merged with the Milky Way. While astronomers suspect it was a small satellite galaxy, its exact size, mass, and composition remain uncertain. The starburst region suggests a sudden influx of gas and dark matter, but the precise details of how this material interacted with the Milky Way's existing structure are still unclear. Was the merging galaxy a dwarf galaxy, or could it have been a larger, more massive system? The answer could reshape our understanding of how galaxies like the Milky Way grow and evolve. For instance, if the merger involved a significant amount of dark matter, it might have influenced the dynamics of the collision in ways that are difficult to model. However, without more data, these possibilities remain speculative. The Hubble observations have provided crucial clues, but they haven't yet resolved the fundamental question of what exactly collided with the Milky Way. Another unresolved issue is the timing and scale of the merger. While the starburst is dated to around 10 to 12 billion years ago, the exact moment within this period when the collision occurred is still debated. Some researchers argue that the merger happened earlier, during the Milky Way's formative years, while others believe it occurred later, when the galaxy was already more mature. This discrepancy has significant implications for how we model the Milky Way's evolutionary history. For example, if the merger occurred earlier, it might have played a more direct role in shaping the galaxy's structure, such as the formation of its central bulge or the development of its spiral arms. Conversely, if the collision happened later, its impact might have been more subtle, influencing star formation rates without drastically altering the galaxy's overall morphology. These differing timelines highlight the complexity of reconstructing events that took place billions of years ago, where direct observation is impossible. The Hubble data has helped narrow down the possibilities, but it hasn't eliminated the ambiguity. The merger's aftermath also remains a subject of debate. How did the collision affect the Milky Way structure and dynamics? Some scientists propose that the merger triggered the formation of the Milky Way's central bulge, a dense region of stars at the galaxy's core. Others argue that the merger might have disrupted the bulge, creating the irregularities observed in its structure today. Additionally, the merger could have influenced the distribution of dark matter within the Milky Way, a factor that remains poorly understood. Dark matter, which makes up the majority of the galaxy's mass, is invisible to traditional telescopes, making it difficult to study its role in such events. The Hubble observations have provided insights into the visible components of the merger, but the invisible forces at play, like the gravitational interactions between dark matter halos, remain largely theoretical. This gap in our knowledge underscores the challenges of studying mergers in distant galaxies, where both visible and dark matter dynamics must be considered. Perhaps the most intriguing question is whether this merger was a unique event or part of a broader pattern in galaxy evolution. The Milky Way's history is not isolated, it is part of a larger cosmic web where galaxies constantly interact. However, the details of these interactions are often obscured by the vast distances and timescales involved. The starburst in the Milky Way might be an example of a common phenomenon, or it could be an outlier. For instance, some studies suggest that mergers between spiral galaxies are relatively rare, while others argue they are more frequent than previously thought. If the Milky Way's merger was part of a larger trend, it could provide clues about how galaxies in the universe evolve over time. But if it was an exceptional event, it might indicate that the Milky Way's history is more unique than we currently understand. This uncertainty highlights the need for more data from other galaxies, where similar mergers might have left behind more visible signatures. The role of star formation in the merger also remains a topic of scientific debate. The starburst region is a striking example of how mergers can trigger intense star formation, but the exact mechanisms behind this process are still unclear. When two galaxies collide, their gas clouds can be compressed, leading to the formation of new stars. However, the starburst in the Milky Way suggests that this process was particularly efficient, with a high rate of star formation that lasted for a significant period. Yet, the details of how the merger's energy and material influenced this process are not fully understood. For example, did the collision create shock waves that compressed the gas, or did the gravitational interactions between the galaxies lead to the collapse of molecular clouds? These questions are critical for understanding not only the Milky Way's history but also the broader role of mergers in galaxy evolution. The Hubble observations have provided valuable data, but they have not yet resolved these fundamental questions about the physics of star formation in such environments. Finally, the implications of this merger for the Milky Way's future remain a subject of speculation. While the merger occurred billions of years ago, its effects may still be felt in the galaxy's structure and dynamics. For instance, the remnants of the merging galaxy could still be present in the Milky Way's halo, where dark matter dominates. However, without more detailed observations, it is difficult to determine the exact nature of these remnants. Additionally, the merger might have influenced the Milky Way's interactions with its neighbor, the Andromeda galaxy. Some studies suggest that the Milky Way and Andromeda are on a collision course, but the details of this future event are still uncertain. Will the Milky Way's past merger with another galaxy provide any insights into its future collision with Andromeda? Or will it remain a separate, isolated event? These questions highlight the interconnectedness of cosmic events and the challenges of predicting the long-term evolution of galaxies. In the end, the Hubble Space Telescope's discovery of the starburst region has provided a fascinating glimpse into the Milky Way's tumultuous past. Yet, it has also revealed the limits of our current understanding. The merger that triggered this burst of star formation remains shrouded in mystery, with many questions about its origins, timing, and consequences still unanswered. These unresolved mysteries are not a sign of failure, but rather a testament to the complexity of the universe and the ongoing nature of scientific discovery. As technology advances and new observations become available, we may one day unlock the full story of this cosmic collision. Until then, the Milky Way's merger mystery stands as a reminder that even the most advanced telescopes cannot see everything and that the universe is still full of surprises waiting to be uncovered. As the Hubble Space Telescope's revelations about the Milky Way's ancient merger history begin to reshape our understanding of galactic evolution, the scientific community is already turning its gaze toward the next generation of observatories and instruments. These future missions are not just about confirming what Hubble has already uncovered, they are about expanding the story, probing deeper into the mysteries of the cosmos, and even challenging the assumptions that have guided our models of galaxy formation. From the James Webb Space Telescope's ability to peer into the early universe to the Nancy Grace Roman Space Telescope's focus on dark matter, each of these tools carries the potential to add new layers to the narrative of the Milky Way's past. Let's explore how these upcoming missions might build on Hubble's findings, what they could reveal about the broader context of galaxy mergers, and how they might even force us to rethink some of our most fundamental ideas about the universe's history. The James Webb Space Telescope, launched in 2021, represents a leap forward in our ability to observe the distant universe. While Hubble has already provided critical insights into the Milky Way's early years, Webb's superior infrared capabilities open a new window into the cosmos. By observing in longer wavelengths, Webb can peer through the dust that obscures young stars and distant galaxies, revealing details about star-forming regions and the distribution of matter in the early universe. This is particularly important for understanding how mergers influence the formation of galaxies like the Milky Way. For instance, Webb could help astronomers identify similar merger events in other spiral galaxies, offering a broader context for the Milky Way's unique history. If these mergers are found to be more common than previously thought, it could suggest that the Milky Way's story is not an outlier but part of a larger pattern in galaxy evolution. Conversely, if Webb's data shows that mergers in other systems occurred under different conditions, it might challenge existing models of how galaxies grow and change over time. Beyond the James Webb Space Telescope, the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, is poised to revolutionize our understanding of dark matter and its role in galactic mergers. While dark matter itself cannot be directly observed, its gravitational influence shapes the structure of the universe. The Roman telescope's wide-field imaging capabilities will allow it to map the distribution of dark matter across vast cosmic regions by studying how it bends light from distant galaxies, a phenomenon known as gravitational lensing. This could provide critical insights into how dark matter interacts with visible matter during mergers. For example, if the Roman telescope detects subtle distortions in the Milky Way's halo that align with the remnants of a past merger, it might confirm the presence of dark matter structures that Hubble's optical observations could not resolve. Moreover, by studying the large-scale distribution of dark matter in the universe, Roman could help determine whether the Milky Way's merger history is typical or if it represents an anomaly influenced by unique dark matter dynamics. Such findings could deepen our understanding of how dark matter shapes the evolution of galaxies and whether mergers are driven more by dark matter interactions than by visible matter collisions. The European Space Agency's Euclid mission, also scheduled for launch in the mid-2020s, complements these efforts by focusing on the nature of dark energy and its role in the universe's expansion. While dark energy is not directly related to mergers, its influence on the large-scale structure of the cosmos could indirectly affect how galaxies interact. Euclid's observations of galaxy clusters and cosmic web structures will help scientists map the distribution of matter over time, providing a backdrop against which mergers can be studied. If Euclid's data reveals that the rate of galaxy mergers has changed over cosmic history, it could challenge existing theories about the timeline of galaxy formation. For instance, if mergers in the early universe were more frequent than in the present day, it might suggest that the Milky Way's merger events occurred during a period of heightened cosmic activity. Conversely, if mergers are found to be less common than expected, it could prompt a re-evaluation of how galaxies like the Milky Way have evolved through time. These insights would not only refine our understanding of the Milky Way's past but also inform models of how galaxies across the universe have grown and changed. On Earth, ground-based observatories are also playing a vital role in extending the legacy of Hubble's discoveries. The Extremely Large Telescope, ELT, currently under construction in Chile, will offer unprecedented resolution and light-gathering power, enabling astronomers to study distant galaxies in greater detail. The ELT's ability to capture high-resolution images of star-forming regions in other galaxies could help identify similar merger signatures to those observed in the Milky Way. By comparing these observations, scientists might determine whether mergers are a universal phenomenon or if the Milky Way's history is unique. Additionally, the ELT's capacity to detect faint, distant objects could shed light on the early stages of galaxy formation, providing a broader context for the Milky Way's merger events. For example, if the ELT identifies a population of ancient stars in other galaxies that match the characteristics of the Milky Way's disrupted satellite systems, it could suggest that the processes observed in our galaxy are part of a larger, cosmic trend. Another key player in the future of galactic studies is the Square Kilometre Array, SKA, a next-generation radio telescope network that will revolutionize our ability to map the distribution of neutral hydrogen gas across the universe. Neutral hydrogen is a critical component in star formation, and its distribution can reveal the structure and dynamics of galaxies. By studying the SKA's data, astronomers might uncover how mergers affect the flow of gas within galaxies, potentially explaining the observed variations in star formation rates. For instance, if the SKA detects widespread evidence of gas being stripped from galaxies during mergers, it could confirm that such events are a major driver of star formation in the early universe. Conversely, if the data shows that mergers have less impact on gas dynamics than previously thought, it might challenge existing models of how galaxies evolve. These findings could also help refine our understanding of the Milky Way's own history, particularly if the SKA identifies patterns in gas distribution that align with the remnants of past mergers. Beyond these missions, the continued refinement of existing observatories, such as the Gaia Space Telescope, will also play a crucial role in expanding our knowledge of the Milky Way's merger history. Gaia's detailed mapping of stellar positions and motions has already provided critical insights into the structure of the Milky Way's halo and the distribution of its satellite galaxies. As Gaia's data continues to be analyzed, it may reveal new details about the timing and scale of past mergers, offering a more precise timeline of the Milky Way's evolution. For example, if Gaia's data identifies subtle variations in the motion of stars that suggest multiple merger events over time, it could indicate that the Milky Way's history is more complex than previously thought. Such findings would not only refine our understanding of the Milky Way's past but also highlight the importance of long-term observational campaigns in unraveling the mysteries of galactic evolution. However, these future missions and instruments are not without their challenges. The vastness of the universe means that many questions about mergers and galaxy formation remain unanswered. For instance, while Hubble has provided evidence of a major merger in the Milky Way's early history, it is possible that smaller, less dramatic mergers have also played a significant role in shaping the galaxy's structure. Future missions may need to focus on detecting these subtle interactions, which could require new observational techniques or the development of more sensitive instruments. Additionally, the complexity of galaxy mergers means that models of how they unfold must account for a wide range of factors, including dark matter, gas dynamics, and the influence of external environments. As new data becomes available, scientists will need to refine these models, potentially leading to breakthroughs that challenge long-held assumptions about the role of mergers in galaxy formation. In conclusion, the future of galactic studies is bright, with a host of upcoming missions and instruments poised to build on the groundbreaking work of the Hubble Space Telescope. From the James Webb Space Telescope's ability to peer into the early universe to the Nancy Grace Roman Space Telescope's focus on dark matter, each of these tools offers a unique perspective on the mysteries of galaxy mergers. As we look ahead, the potential discoveries from these missions could not only confirm what we already know about the Milky Way's past but also expand our understanding of how galaxies across the universe have evolved. Whether these findings reinforce existing theories or challenge them, one thing is certain: the story of the Milky Way's merger history is far from complete, and the next chapter is about to be written by the next generation of scientific exploration. So there's this ancient puzzle about our Milky Way galaxy. For decades, astronomers have wondered, in its early years, did it grow by peacefully absorbing smaller galaxies, or did it erupt in violent mergers that reshaped its structure? The answer has been elusive until Hubble stepped in. Recent observations from the James Webb Space Telescope and Hubble's deep field imaging have finally cracked this mystery, revealing a story of cosmic chaos and quiet evolution. Let me break it down. First, the Milky Way's early history wasn't as calm as once thought. Studies of ancient stars in the galaxy's halo, those faint, scattered stars that orbit far from the galactic center, show evidence of a massive merger billions of years ago. These stars, older than the Sun, have chemical signatures that don't match the Milky Way's usual star-forming patterns. That suggests they were born in a different galaxy, torn apart and absorbed by our own. But here's the twist: the merger wasn't a one-time event. Hubble's data hints at multiple smaller collisions over hundreds of millions of years, each adding fuel to the galaxy's growth. This challenges the idea that the Milky Way's structure was built slowly through gentle accretion. Instead, it points to a more dynamic, turbulent past. Second, the clues came from unexpected places. By mapping the motion of distant satellite galaxies like the Large Magellanic Cloud and the Sagittarius Dwarf, astronomers noticed strange distortions in their orbits. These aren't random, they're the scars of past collisions. Hubble's sharp vision allowed scientists to trace these paths back in time, reconstructing the Milky Way's violent encounters. One particularly dramatic event, dubbed the Gaia-Sausage Merger, involved a dwarf galaxy about 10 times the mass of the Large Magellanic Cloud. Its collision with the Milky Way threw streams of stars into the galaxy's halo, creating the ripples we see today. But here's the kicker: the merger didn't destroy the Milky Way. Instead, it infused it with new material, fueling star formation and shaping its spiral arms. This suggests that mergers aren't just destructive, they're essential to a galaxy's evolution. Third, these findings have broader implications. If the Milky Way's early history was so turbulent, what does that mean for other galaxies? It challenges models of galaxy formation that assume a more passive growth. The Milky Way isn't a solitary island, it's part of a cosmic dance, colliding and merging with others to build the grand structures we see today. And this isn't just about the past. The same processes are still happening. The Milky Way is currently merging with the Andromeda Galaxy, a collision that will reshape both in about 4 billion years. So, what's the takeaway? The Milky Way story is one of resilience and transformation. Its early mergers weren't just violent, they were vital. They forged its structure, enriched its stars, and set the stage for life as we know it. But the mystery isn't fully solved. There are still questions. How many mergers occurred? What role did dark matter play? And could similar events explain the strange features of other galaxies? If you followed this deep dive, you've seen how cutting-edge telescopes like Hubble and JWST are rewriting our understanding of the universe. But science is a journey, not a destination. If you enjoyed this episode, hit subscribe for more space mysteries, and drop a comment with your own theory or question. Maybe you've got a hypothesis about the next big merger in our cosmic neighborhood? Let's keep exploring together.